and what you're listening to there is Swan Lake by Tchaikovsky. Welcome to Talkcast episode 121. Chiara Marletto in The Science of Can and Can't, chapter 6, titled Work and Heat, begins that chapter by recounting how, as a child, she had a music box which one would wind up and a little ballerina would dance while that music played. Strangely, I had exactly the same thing. No, as a child, I didn't personally have a music box like this as such, but my mother did, which was in our house as I grew up. It was a jewellery box. Same idea. You wound it up and a little dancing ballerina danced to a tune. And it played, I think, a different tune, not exactly Swan Lake. Anyway, at the beginning of chapter 6, Chiara explains how this mechanism works by turning a key, winding the thing up. The box is charged up, so to speak, with mechanical charge, energy stored in the elasticity of a spring-like mechanism that slowly does the work of moving the pieces and playing the tune. Today I'm doing lots more reading than normal, I guess, because the ideas in this chapter, in particular, they're new. And I'm extending what is new here from what I said in episode 119, all about the thermodynamics that everyone already knows who's studied thermodynamics before. So I'll begin the reading today with the introduction to this chapter that Chiara has written. And she writes, quote, "In this chapter is where I discuss the conservation of energy as a counterfactual principle about impossibility, 3 different kinds of irreversibility in physics, statistical, forgetful, and counterfactual, where I provide a counterfactual second law based on an exact distinction between work and heat, and where you encounter the Universal Constructor, a machine that can perform all transformations that are physically possible." End quote. Now, in my readings here for Talkcast, I'm not going to do all that. In particular, I'm not going to look at the 3 different kinds of irreversibility in statistics. In particular, I'm not going to look at the forgetful kind. Now, as I'll be doing a lot of reading today, I'm trying to cut out as much of the chapter as I possibly can. And so, as I say, Chiara begins the chapter by explaining the mechanical operation of the ballerina in a music box and the sound coming out of the music box. So I'm skipping the basics of that, and I'm going to pick it up where she writes, quote, "Where does that motion originate? At first sight, it comes from the user who turns the winding key. However, if you go a little deeper, this seems to be the start of an infinite regress, which has happened repeatedly in this book as signalling a problem in the traditional conceptions explanations. There is no end in sight if you go down this line of inquiry, because you could ask the same question of the motion of the user's hand. Where does that originate? Also, innumerable other mechanisms could equally well wind up the box. For instance, a small mechanical engine attached to the winding key could do as well as the user's hand. To understand, you need to ask a more fruitful question. What is the mechanical charge made of? What kind of stuff powers the music box when you wind it up? The stuff that charges the box is what physicists call energy. The term comes from a Greek word popularized by Aristotle, whose original meaning in Greek is capacity to work. Nowadays, what we call energy in physics is even more sharply defined than in Aristotle's time. It is an abstract property of physical systems that must be subject to substantial constraints. As we know, the most important of these constraints is the law of conservation of energy, requiring that the energy of a system can be changed only at the cost of changing the energy of some other system by the same amount. The law of conservation of energy is about counterfactuals, for it requires that it be impossible to change the energy of a system without any side effect. Given that all laws of motion must conform to the conservation of energy, those already known, and those yet to be known, the conservation of energy is more general than any specific dynamical law. Also, it is intended to apply to any system in the universe. It rules minuscule particles such as electrons and protons, heat engines that propel aircrafts and spaceships, and the mitochondria powering our cells. It applies to anything and everything that has an energy independent of its scale and size." End quote. Just my reflection on that. This idea of scale independence is really, really important here. What it means is that the law, scale independence means something applies whether the thing is small or big, independent of its scale, how much bigger you make it, whether it's a single atom or a conglomeration of atoms. It's not like laws of physics should apply to big things and not small things. Although this is a misconception that sometimes gets around. The laws of quantum theory should apply everywhere, no matter the size of things. And in reverse, so to speak, so the laws of thermodynamics, which are found to apply to heat engines, big things, should also apply to small things as well. And in both cases, quantum theory and thermodynamics, it must be the case that the laws are scale independent. They apply no matter the size of the thing. And the thing is, they do, I would suggest. But our imperfect knowledge of them seems to suggest, at first glance, that the quantum laws apply to little things and thermodynamic laws apply to big things. Well, not always, but the idea here is that this is what's going on in the mind of some people. And by the way, it's also why you have people like David Wallace who write about the emergent multiverse. Okay, the idea that these laws of quantum theory do indeed apply to large ensembles of particles, indeed the entire universe. And that's what we would say. But you hear other popularizers and other physicists talk about how, well, quantum theory are just the laws that apply to the very small. And that's not the case. They're universal. They apply everywhere. It's just that from our perspective, certain things appear to be the case, but appearances can be deceiving. But if things do appear in some way, and that's a problem, which it is here, then we should seek to solve the problem. In the case of the second law, that's certainly a problem, because it appears to apply to big things, but at the small scale, at the level of individual atoms, the laws appear to be reversible. But the second law is about irreversibility, which is what Chiara is going to come to in this chapter and what we're going to talk about. But just here, in what I've just read, Chiara has mentioned the first law, never mind the second. And on this, I have a stop press, which has never happened before. Older listeners will know what stop press means. Stop press being what used to happen to newspapers. They'd print the physical newspapers and send them out all over to the newsagents and shops, and the paper boys would deliver them. Always paper boys, never paper girls. And if partway through the printing of the newspapers, something of note happened, they'd stop the printing presses. Stop press. I remember there was a box left empty on the last page of newspapers in Sydney anyway. It read stop press, and beneath it there was a space to insert news that appeared during the press, during the printing of the papers. I think it was done in red ink, if I remember. Okay, silly diversion there. My stop press for this is that as I was making this very episode, Chiara Marletto published an official paper about how constructor theory can be used to illuminate a connection between information and the first law of thermodynamics. Now, this is in addition to work she'd already done, and what this chapter is primarily about how the second law can be better understood given constructor theory, and underlines the known link between work and information, given constructor theory. Now, I'm just going to mentally check off the fact that that paper exists now. I read through it, but I cannot do it justice. I cannot turn it into a succinct few sentences here for public digest, I suppose. That will take some work, and perhaps I can leave that for an actual discussion with Chiara herself, or I can make an additional episode all about that. But it may just get a little too technical. This is going to get technical in places enough, so we'll just mentally check off the fact there has been yet another paper published on the 27th of May 2022 in the Journal of Physics Communications, titled The Information Theoretic Foundation of Thermodynamic Work Extraction, and has there statements about the first as well as the second law. Today we're focusing on the second law, but just to say, there is this new paper out there all about work, information, the first law, and constructor theory. Back to this episode, where we've just talked about how the first law applies to everything and is scale independent. Chiara goes on to say, quote, "This seemingly innocuous requirement has sweeping consequences. First, it implies that the energy of a system cannot increase or decrease unless energy is supplied from or absorbed by something else. This allows us to account minutely for the whereabouts of energy as it transits from one system to another. When it escapes from here, it must have gone over there. It can't disappear or pop into existence. For example, the music box cannot get charged spontaneously without something else providing the energy. The winding of the key, Likewise, the battery of a smartphone does not get replenished if the device is switched off and not connected to the power supply. Okay, I'm skipping a number of chapters, picking it up where she writes, quote, "The conservation of energy implies the startling prediction that, at each step along the chain, if one accounts for all the systems involved, one shall find, overall, the same amount of energy initially given to the winding key. Such is the inescapable accountancy set by the law of conservation of energy, and it is based on the counterfactual property that it is impossible to change the energy of a system without side effects being produced." End quote. Yes, so here we have the winding of the key which sets the music box into motion, and the energy that's there at the beginning from winding the key, stored in the winding mechanism, a spring of some type, is then transferred into work which moves the ballerina around, and work which sends sound waves out into the atmosphere. And also some heat's produced as well. But all of the energy that's produced was there originally in the winding of the key. Again, skipping and picking it up, where Chiara writes, quote, "The second law distinguishes between two types of energy transfers, and the distinction is rooted in counterfactuals. One type of transfer is reversible. One can use these energy transfers to perform work on a variety of physical systems, such as the brass winding key of the music box, or a flywheel, or a piston, and then undo the transfer completely, retrieving the energy in full, with no irreversible losses. The systems supporting these energy transfers are fully interoperable, just like the systems in the music box. The other type of energy transfer is irreversible. Once the transfer happens, it cannot be fully undone. Part of the capacity to do work is lost along the way. A classic example, brakes on a bike. When you brake, you apply resistance against the rotation of the wheel and brake initially have a certain energy, and they come to a stop. The brakes and the wheel itself have heated up. Why? The energy that was in the motion of the wheel and the bike has now gone into the thermal motion of the molecules composing the wheel and the brakes, and it is practically irretrievable. I shall revisit practically later. The same holds for the energy of the vibrations bringing the tune of the music box all the way to our ears. Once the music is heard, it is very hard to bring that energy back into the box's mechanism. The chemist Peter Atkins has frequently said in his masterly books about the foundations of thermodynamics that work and heat are not substances, just as information is not a substance. They refer to modes of transfers of energy. I call the reversible transfers work-like. The transferred energy that can be reused ad infinitum to initiate or to stop controlled ordered kinds of motion. I call the irreversible transfers heat-like. The second law requires some energy transfers to be heat-like once they happen. It is impossible to recycle some of the energy involved in them. That energy can no longer be used fully for a work-like transfer. Only some of it can." End quote. So this distinction between work-like and heat-like is a key of this constructor theoretic view of the second law. And the constructor theoretic view is obviously also couched in terms of this idea of a constructor. So the second law is about the fact that there is no object possible, we're going to come to this, no object possible, no constructor, that can do certain processes in reverse. We can't capture the lost heat, for example. There's no constructor that one can build, or that can be built, that could enable the recapture of that heat so that useful work can be done. Why? Because there is no physical transformation possible. So no constructor can be built, so therefore there's no physical transformation possible. This is Constructor Theory. And why is that? Why is it that there's no constructor able to do this? Why can't we build that device? Why? Well, that's just the way things are. That's the whole point of the laws of physics. We are now in a world where we're asking, if you're asking that question, why can't we have photons travelling below the speed of light? Well, that's just what they do. They travel at the speed of light. Now, anyone who listened in to episode 119, where I went through an introduction to thermodynamics, will recognise that name, Peter Atkins, one of the most famous thermodynamicists, physical chemists of our age, who's written a lot of the classic texts on exactly this stuff. It was interesting to hear Chiara, actually, in one of her interviews she did with Logan Chipkin. And if you can find those out there, look up Logan. He's on Twitter, and you just Google his name, Logan Chipkin. And he has interviewed Chiara. And they talked there, well, Chiara brought up about how Peter Atkins himself has jokingly credited Chiara with the discovery of a new kind of entity, information, Enformation. Something with the properties of both energy and information. That is the stuff that can be stored, so to speak, on work media, which we're going to come to. Now, I'm not a physical chemist, and I'm not a theoretical physicist, so I don't know how deep that joke runs, how seriously we can take that joke, or whether one day there might actually be this thing called information. I'm not sure. Anyway, I'll get back to the book, and Chiara writes, quote, "The second law of thermodynamics operates in a rather impressive way. In tandem with the principle of the conservation of energy, it provided the theoretical foundation for heat engines, which powered the incredible progress that occurred during the Industrial Revolution. But when it comes to explaining exactly what the second law says about the physical world, the issue is not as clear as for the conservation of energy. It is so complicated and subtle that physicists over the decades have proposed numerous inequivalent formulations of the second law. Each has its notion of heat-like and work-like transfers of energy, and they are different from each other. Still, all these different formulations concur on a few striking consequences concerning the thermodynamics of heat engines. The second law is thus a pillar of the edifice of theoretical physics, but we are not quite sure what it means." End quote. Yes, and this is why popular science in particular is so enamoured with the second law. I'd be hard-pressed to find one of Paul Davies' books that doesn't mention it. In fact, I'd be hard-pressed to find any popular science book in the general sphere of physics that doesn't mention it. Physicists love discussing the second law because it has this mysterious characteristic that other laws don't, namely irreversibility. It seems like the processes that the second law governs happen one way, but there's no time-symmetric way of reversing them, simply in the other direction. Although it should be, because every other law, the dynamical laws in particular, do have this time-symmetric property. They run perfectly well forward in time as back in time. And if you took a video, as I said, of the process that was going on, it was, subatomic, no physicist would be able to look at that video and say, oh, that's the forward time direction, that's the reverse time direction. It's impossible to tell. Or is it? Well, this is the whole thing about the second law. Maybe there's something hidden, some information hidden there that tells you which way is forward in time. In particular, maybe thinking about these things in terms of dynamical laws is not the way to go. Okay, skipping a few paragraphs, and I'll pick it up where Chiara writes, quote, "The problem is that the second law requires some irreversibility. Incidentally, that is also why it is so fascinating. Irreversibility is at the core of various phenomena that are ubiquitous in physical reality. The birth, development and death of organisms, the growth of complexity in the biosphere, the increase in sophistication within our civilization, the creation and destruction of knowledge, the irreversibility requirement of the second law brutally clashes with the laws of motion ruling the elementary constituents of matter. Remember, I said in chapter 4 that the laws of quantum theory are reversible. If they allow for a transformation, the reverse transformation must also be possible. The laws of general relativity, the other most accurate description of physical reality we possess, are reversible too. If there is a trajectory that takes a system from A to B, there must also be one that takes it from B to A. Microscopic constituents of matter must operate in this reversible manner because they obey these laws of motion. The problem then is, how can the second law require that some energy transfers are irreversible and be compatible with the reversibility of the laws of motion? And I'm skipping a part. And she goes on to say, is there a unique picture of physical reality that can reconcile reversibility and irreversibility? Physics does not yet have a definite answer to this question, let alone a unique one. There are a few proposed answers, but each is still controversial. Ultimately, it is because theoretical physics is trapped in a world without counterfactuals. With counterfactuals, one can reconcile the reversible description of the laws of motion and that of the second law at all scales. To see how, I shall first take a closer look at the irreversibility of heat-like transfers. Imagine a playground, and in that playground a seesaw. A seesaw consists of four main systems. Two seats of approximately equal mass, a rigid, long, sturdy bar joining them, slotted on a pivot, placed at its midpoint. We need two children to play. A child sits at each end so that one goes up as the other goes down, by gravity, depending upon which child weighs more. Added fun comes if the children attempt to go as high in the air as possible as they take turns pushing their feet against the ground. Let's simplify the picture a little. First, imagine that instead of the children, there are just two springs firmly secured to the ground underneath each end of the bar. Also imagine that both ends, call them A and B, have the same mass. The seesaw in the neutral position corresponds to the bar being perfectly horizontal above the pivot. Still. Now imagine you push one of the ends, say A, in the upwards direction. Up it goes, while the other end, B, goes down and compresses the spring as much as allowed by the conservation of energy. The energy given by your push is now transferred entirely to the spring. Then the compressed spring gets decompressed by its completely elastic nature, thus giving back the energy to the B end of the seesaw, which therefore goes up, and A goes down, compresses the spring in turn, and so on, end quote. Chiara goes on to explain over the next few paragraphs about how, well, if there's no other effects going on, then this just goes on forever. You have a perpetual motion machine of a kind, in theory. But in reality, we know that these things come to a stop. We have what's called a damped oscillator. Friction gets involved. But what is this friction? Where is this energy being lost? Why should such a mechanism like that, a seesaw with springs at either end, not just keep on going on forever? Well, Chiara goes on to explain. Quote, "For a start, there are countless molecules of air continually bouncing off the bar as it goes up and down. Then the spring is also not perfectly elastic. The energy transmitted to it by the bar is not entirely returned when the spring gets decompressed. Some energy goes to waste away from the seesaw oscillations. For example, it is absorbed by the atoms of the spring, which increase their internal vibrational energy. So there are several more interactions to take into account to explain where the energy goes in real life seesaw. All these interactions take a little energy from the combined motion of the seesaw and the springs. That is why, if a real-life seesaw is set into motion and then left alone, it eventually comes to rest. Overall, though, energy is still conserved. When the seesaw comes to a stop, the energy given by the push is stored in the air molecules and in other particles inside the spring and the bar. They are all a little warmer, more energetic than before. Here is the point where irreversibility creeps in. In a world where all elementary interactions are reversible, once the energy has gone into molecules of air and vibrational motions of atoms, it becomes tough to bring it back in practice. Such kinds of energy transfers are those the second law labels as heat-like, generally regarded as irreversible, just like in the case of brakes or the music box." End quote. Okay, I'm skipping a number of paragraphs where Chiara talks about the status of the second law. Is it really that fundamental? And I'll just read one of the important paragraphs here as to what she says about this. Quote, "If reversing heat-like energy transfers were just very hard to achieve, but ultimately possible, the second law would not really be a fundamental law. In fact, there would be no reason for physics to distinguish between work-like and heat-like. There would be no irreducible irreversibility. All energy transfers would be work-like, that is, reversible, only a little harder to achieve in the reverse direction compared with the forward direction. The second law and its prescribed irreversibility would just be the description of our current technological limitations, which of course are not fundamental. These limitations can be improved upon by investing enough resources into it." On this question of whether the second law is fundamental, physicists are currently divided into two main camps. One camp says that it is not fundamental. There are only reversible laws governing the microscopic interactions of particles. With enough technological resources, the reversible dynamics could always bring all energy back to where it came from, and one could then reuse the energy to do work. This would imply that the limitations imposed by the second law on heat engines are just a rule of thumb, telling us that it is hard in practice to reverse specific interactions, but these limitations could be lifted ultimately by improving our technology. According to this camp, the second law does not need to appear in the manual for the universe. The other camp claims that the second law is fundamental, that there can be a formulation of the second law that is universally true and still compatible with the reversible dynamics at all scales. Can this be so? Various paths to reconciling irreversibility with reversible laws of motion have been proposed to support this idea. None of them really works to the end of creating a universal exact law. They ultimately all concede that irreversibility only appears as some sort of approximation, but that is not fundamental. Only one of these paths is based on counterfactuals, as I shall explain. It is the only one that has some potential to be successful in this endeavour. I shall go into a little detail about these paths because they are smart ideas, even if they end up with mixed success in regards to producing an exact second law. Understanding the other approaches is indispensable to grasping the superiority of the approach with counterfactuals. End quote. Okay, I'm skipping a number of paragraphs. I might just mention the section where Chiara talks about why she doesn't talk much about entropy. Entropy doesn't come up in the constructor theoretic view of the second law. And the reason is because it's a statistical law. It's kind of an approximation when we talk about entropy. As Chiara says, quote, "The statistical mechanical law cannot even aspire to be exact or universal. The configuration maximizing the entropy is not the only one guaranteed to occur. It is the most probable. All other configurations can still occur, but it is not said when and how, only that they are less likely. The fundamental reason why the statistical second law cannot be exact is that the dynamics regulating the exchange of energy between, say, iced tea and the surroundings are reversible." End quote. So, of course, that's nice, right? This idea of entropy is disorder. And what the second law says, phrased in this way, is that disorder tends to increase in the universe. Tends to. It's the most probable, as Chiara would put it there, the most probable way in which the universe evolves is that it evolves towards increased entropy, increased disorder. But this is not a guarantee. But with laws of physics, you want a guarantee. These things are incontrovertible. These things tell you what will happen, not what will probably happen. And we've talked about that on TalkCast before, when we've broken down David's talk on probability. So I refer people to that episode, which, if you're interested, is episode 111 of TalkCast, where I go into David's talk on probability, where specifically this kind of issue arises. You know, the laws of physics tell you what actually happens. They don't tell you what probably happens. And so this is one of the reasons why, one of the motivations for this entire constructor theoretic view of the second law. Because other versions of the second law, involving, for example, entropy, are about what probably happens to ensembles of particles and to the universe. But we want to know what will happen, not probably. So not only does Chiara talk about why that doesn't work, that statistical view of the second law, talks about another one as well. So I'm skipping all of that, quite a number of pages here. And instead I'll pick it up where Chiara writes, quote, "Just like Goldilocks in the Three Bears house, after trying two paths that do not work, we land on the third path to irreversibility, based on counterfactuals. This path is not just right, it too has problems, but it is more promising than the other two, which are instead based on the traditional conception of physics. To set off down this path, let's trace the same conceptual steps that led the superb physicist James Joule to perform a crucial experiment in the early days of thermodynamics. What he conjectured and verified experimentally was that while it is possible to heat up a volume of water by stirring it only mechanically, it is impossible to cool it down by those same means. You can see that I am now talking about counterfactuals. The language regarding possible, impossible transformations belongs to the science of can and can't. Let's return to a glass of iced tea. Joule would have preferred a glass of beer, as he was also a brewer, but I shall stick with the tea. It can't do any harm. Imagine you stir the tea vigorously, mechanically, say with a spoon. This stirring provides the molecules of water with more energy. Imagine that the glass is somehow perfectly isolated from the rest of the environment, and no energy, other than the energy of the stirring, can be exchanged with the environment. What you will find out is that the tea in the glass ends up in a hotter state at the end of the stirring. On the other hand, no matter how hard one tries, the temperature cannot decrease through stirring only. In this scenario, that transformation is impossible. Of course, if the glass is not isolated, you can stir the tea to cool it down by facilitating exchanges with the air in the environment. However, here I imagine the cup to be entirely isolated. This kind of irreversibility prescribes that sometimes a transformation, such as heating some amount of water, is possible by mechanical means only, i.e. using the stirrer. But the reverse task is not possible by using those same means, though it may be possible by other means. Work-like energy transfers are those corresponding to transformations that can be performed by mechanical means only in both directions. Pausing there, my reflection, just going back, it's worth saying that again. Work-like energy transfers are those corresponding to transformations that can be performed by mechanical means only in both directions. And going on. Heat-like transfers correspond to transformations that are possible by mechanical means in one direction only, but are impossible in reverse, using the same means and nothing else. As you can see, this path to irreversibility is about possibility of certain transformations and impossibility of their reverse. It is about counterfactuals. This approach to the second law is due to Lord Kelvin and Max Planck. It does not talk about the most probable free evolution of a physical system in contact with an environment, or about what trajectories a system accesses once you discount some of its details. End quote. Just pausing there, my reflection. Yes, so on this experiment with Joule and stirring and so on and so forth, again, I refer the listener to episode 119 if you are unsure of any of these details and you want to hear the classic way in which some of these things are described to see what we're getting at here and the importance of what we're getting at here. Just go back to that episode and you'll find me discussing Joule's experiment there and the high school version of this kind of thing, the high school explanation of this kind of thing as well. So here we're emphasizing Kelvin and Planck's invocation of what can be called, a version of constructor theory. This idea we've got possible and impossible stuff going on. The work-like means that it's possible in both directions, but the heat-like, it's possible in one direction, but impossible in the other direction. This is wonderful. So let's keep going with what Chiara says here. Quote, "The fascinating revelation is that this kind of counterfactual irreversibility is compatible with time reversal symmetric laws without requiring any approximation, because even under perfectly reversible microscopic laws, it is possible to have some device that can perform a transformation in one direction by certain means. Example, there can be a machine, such as an automated stirrer that heats up a liquid by mechanical means only, whereas it is impossible to have a device performing the task in reverse, with the same means. For example, cooling a liquid by mechanical means only. Crucially, reversing the laws of motion of the elementary constituents will not turn the forward device, performing a transformation from A to B, into a reverse device, performing the inverse transformation from B to A. Even if the elementary constituents of both devices obey reversible laws, the forward device does not necessarily imply the existence of a reverse device. Even if their elementary constituents behave reversibly, you can have that the forward transformation is possible, whereas the inverse transformation is impossible. This irreversibility is different from the statistical irreversibility, which requires that the forward trajectory of a freely evolving system is overwhelmingly more likely than the reverse trajectory. It is also different from the forgetful irreversibility, where one trajectory happens whereas others do not, only if one neglects some details of what is going on. The latter statements can be only approximate, based on probabilities or arbitrary neglecting procedures. By contrast, the statement that the transformation is possible and its reverse is impossible is exact. It involves no arbitrary forgetting or probabilistic approximations. This counterfactual path to irreversibility and to formulating the second law is exact. Just pausing there, my reflection. Well, that's the punchline. There's your punchline. That is the way in which the second law can be formulated. And I love that, this idea that work-like transformations, possible in both directions, heat-like transformations, possible in one direction but not possible in the other. And there's no such device that can be created, can be constructed in order to allow the transformation to occur in the reversible direction. Chiara goes on to say, quote, "However, as it stands, this approach suffers from a serious problem. It does not explain what mechanical means are. Its domain of applicability is therefore undefined. A stirrer qualifies as mechanical means, so do an ideal spring in a suspended weight, but does, for instance, an atom in a well-defined state of energy count as a mechanical means as well? What about a current looping in a superconductor, or a photon with a well-defined frequency? Without a criterion to decide what counts as mechanical means, the statement, this transformation is possible with mechanical means only, but its reverse is not possible with those means only, is exact, but does not say anything specific about the universe. A second law expressed along these lines remains unclear, so it cannot be a useful addition to the manual for the universe. For it to be clear and useful, it needs to explain what mechanical means are. Here is where the interoperability property, which I hinted at while describing the music box, comes in handy. The solution comes in beautifully, once more, through the counterfactual approach. So remember, end quote, just remember what interoperability is all about. It's this notion of substrate independence. Now, Chiara goes on, and I'm skipping a few paragraphs here, to explain a little about what this mechanical means is. I'm just skipping over that and getting more to the meat of the matter, where she writes, quote, let's resort again to a variant of our seesaw example, involving two weights hanging on either side of a pulley at some height above the ground. The first important point to notice is that different heights for the weights indicate different values of energy for each, because I am imagining that, as in the seesaw example, a gravitational field is present, which means, following a simple logic based on Newtonian mechanics, that the higher a weight is suspended above the ground, the higher its potential energy. If this sounds counterintuitive to you, think of the familiar case of water falling from a height in a waterfall. The higher the fall, the more energy is carried with the water. Okay, so end quote. So here we've got an idea of weights on a pulley, and we can call the weights A and B. And if A is higher than B, then A has more energy than B. This is what we're talking about here. And the weights can be moved. The pulley can be moved so that B will go higher than A, and so on and so forth. Work can be done. We can have a seesawing transformation of energy being added by someone doing work on it. And we could have a situation where A and B are at the same height, or maybe A is higher than B, so A has more energy than B, or maybe A is much, much higher than B, so A has much more energy than B, or maybe B is higher than A, so B has more energy than A. What on earth has any of this got to do with anything? Well, we're introducing the concept of a system which has different energies able to be stored in the system, which look a lot like information, don't they? Because they're different states for this system. This system, which is based upon energy, the potential energy of suspended weights, also looks kind of like the way in which information could be stored. And we can move the pulley and move the weights, therefore, to change the states of the system. And in theory, this thing could be done in a friction-free way. And so you could move these weights mechanically around. And therefore you have this concept of mechanical means. As Chiara says, quote, the mechanism itself, the system of pulleys and weights, remains unchanged, which is what makes it behave like a catalyst, as I defined in Chapter 5. A system that can enable a transformation and retain the ability to enable it again. So now it is easy to express what mechanical means are. They are all systems with different energy states having the crucial property that the seesawing transformation I have expressed is possible. And I'm just paraphrasing what she goes on to say. She uses notation, so I'm going to try and get around using the notation. She talks about how, well, you've got these two weights A and B. And if A is higher than B, well, that's one state. But if B is higher than A, that's a different state. And if A and B have the same height, well, that's a different state again. You have all these different states possible, different values of energy of A and B. But this is just representative. It could represent, different energy configurations for an atom, as she says, or any other system that could store potential energy like this. And I'll pick it up where she says, quote, I have characterized mechanical means with a counterfactual property. They are the physical systems with the property that the seesawing transformation defined above is possible. And when, end quote, what we mean by the seesawing transformation is just like, if you've got these two weights over the pulley, A and B, A is higher than B, well, they can be seesawed such that B is higher than A. So the total amount of energy in that system is the same. It's just that you've transferred potential energy from one place to another. She goes on to say, quote, to highlight the fact that this characterization embraces far more general things than mechanical means, such as springs and weights, I shall call systems that have that property work media. They include weights and springs, but also microscopic particles like atoms and qubits in particular states, but not glasses of water or cups of tea at a given temperature. The fact that they permit a seesawing transformation is the counterfactual property that singles out all systems that can undergo work-like reversible energy transfers among one another. It is what we needed to complete the formulation of the counterfactual second law to make its domain of applicability well defined. A work-like transfer of energy is one that transforms a physical state from one state to another and back again, requiring a change in energy on work media only. For instance, the ideal frictionless seesaw implements a work-like energy transfer between two weights on each side because each of them qualifies as a work medium. On the other hand, if one of the two transformations, going from A is higher or B is higher, is impossible to perform with side effects on work media only, the energy transfer is heat-like, that is, irreversible. So going back to the Joule example, heating up a cup of tea by stirring involves a heat-like transfer of energy from the surroundings because it is not possible to perform the transformation in reverse, cooling, by mechanical means only. The counterfactual second law then can be expressed concisely and with no approximations as requiring that there must be heat-like transfers in the universe. In this form, the second law can be applied to all scales independent of the kind of system. It is exact. Bingo. Okay, end quote. Going back, just rereading that again. What's this counterfactual second law? How can it be expressed concisely with no approximations? It is this. There must be heat-like transfers in the universe. Full stop. There must be heat-like transfers in the universe. There are these processes which are irreversible. It's impossible not to have simply reversible processes in the universe. Might be another way of putting it in the counterfactual way, but as it is expressed there must be heat-like transfers in the universe. What are heat-like? Heat-like transfers are possible in one direction, but the reverse is not possible. Let's go on. Chiara writes, quote, "The traditional macroscopic second law was successful with macroscopic heat engines, such as those in trains and cars. But this extended counterfactual second law has the potential to apply to their nanoscopic equivalent entities. For instance, it applies to the nanoscopic electric devices in your phone, to the qubits in quantum computers, to the natural and artificial molecular assemblers that operate at the scale of our cells. The definition of work media, that they are all systems on which a seesawing transformation is possible, is wonderfully general. It applies to a weight suspended in a gravitational field, as well as to an atom with different energy levels available for its electrons, and it does not depend on the scale, which means it doesn't depend on the size. What remains to be done in this case is to derive predictions from this extended counterfactual second law in the domains that the traditional formulations cannot cover. This kind of research, which requires a joint effort of both theoretician and experimentalist, is underway. If it goes well, it will provide us with groundbreaking technological outputs which will harness the properties of microscopic systems in order to realise nanoscopic heat engines and assemblers." Okay, skipping a short paragraph. Chiara writes, "Systems that can be used to perform work-like transfers of energy must also be able to store information. They must have at least two distinguishable states, A and B, that can work as a bit. Energy states such as A and B that are usable for work-like transfers are distinguishable. They can store information. That's what distinguishes them from energy states enabling heat-like transfers, which need not be. The fact that any system usable to perform work-like energy transfers can also be used to store information is a profoundly unifying link between information theory and thermodynamics, the link between heat engines and computers. This unification is not just elegant. It is also extremely useful in practice, just as Turing's theory of the universal computer was essential to develop the information technology that now sustains our civilization. The path just trodden connecting information and thermodynamics through work media leads us to consider a fantastic possibility. There could be a more general branch of physics encompassing both information theory and thermodynamics, providing fundamental universal principles constraining laws of motion that we know and that we do not know. Just as the theory of information led to the theory of universal computation, this theory I am envisaging could be the seed for designing a machine that generalizes the universal computer, which scientists call the Universal Constructor. This machine was first conceptualized by the polymath John von Neumann. It has in its repertoire all physical transformations that are physically permitted, not just computations, but general constructions, including thermodynamically allowed ones, cooling down various systems, biological ones, self-reproduction and related biological functions, and much more, all in one single machine. It can be thought of as the ultimate generalization of a 3D printer. When inserting an appropriate program into it and giving it enough raw materials, the Universal Constructor would construct out of them any system that is permitted by the laws of physics. The realization of a Universal Constructor, though presumably very far in the future, could have epoch-making consequences comparable in reach with those of the Universal Computer, which paved the way to the current information technology era. Formulating an exact theory of thermodynamics, as I have done in this chapter, is the first step necessary to construct the theory of the Universal Constructor, opening up avenues that will provide a radically new perspective on the physical world. End quote, end of the chapter. And that is a great vision there at the end of technology to come, but I haven't spoken to Chiara or David about this. But it might be worth mentioning here, there is a kind of connection between personhood, what a person is, people in other words, and the existence of a universal constructor. Now, I don't know what that is precisely. No one knows what that is. It's rather like the connection between the universal computer and a person. Now, a person is not to be identified with a universal computer. You can't say a person is a universal computer, full stop, because that's not so. For one thing, a universal computer, or at least all other universal computers, are objects that follow instructions or programs. You give them a task and they do it. They do not disobey. They don't have the choice of disobeying. This is not like a person. But that said, a person can choose to emulate whatever it is that a universal computer can do. Should they choose to? Of course, not reliably necessarily. People end up changing their minds, unlike all other computers that have no mind to change. Well, that's my opinion anyway. Computers have no minds. But then mind itself, mind of the kind that we have, that a person has, is itself a kind of computation. So it does get subtle here. Whatever the human mind is a kind of software running on the brain, which is the hardware, and regular listeners to Talkcast will know this is my hobby horse. So I don't want to risk losing people in frustration as I start beating that hobby horse to death once again, so to speak. But with the Universal Constructor, it is analogous to the Universal Computer, but whereas the Universal Computer is the device, the computer, which is able to do the task of any other computer, or in other words, its repertoire includes that of all possible computers, all physically possible computers in our universe. If it's computable, then the Universal Computer can compute it. And the laws of physics are themselves all computable, and they govern everything, including the operation of human brains. Hence, a Universal Computer could emulate a human brain and run a mind as well. So that's that argument. Likewise, a Universal Constructor would be able to construct anything that is constructible. If it can be built or made or whatever word you want to use, if it can be transformed from this into that, then the Universal Constructor, given the requisite raw materials and, crucially, the plan or the algorithm, the program for doing so, then it could do it. So this shares something with a person, but it would be wrong to say that a person is a Universal Constructor, because a Universal Constructor slavishly follows a program. It doesn't have a choice in the matter, rather like a dumb computer or so-called artificial intelligence, what's called artificial intelligence today. Again, the distinction between AGI, artificial general intelligence, and AI looms here and underscores why AGI is not just advanced AI. In fact, it's better to think of AGI, or just general intelligence in general, like us, as being the opposite of AI. AGI and AI are actually like the opposites of one another, more than the former, AGI being an advanced version of the latter. AI is something, the AI as we have it now, what people call AI, it's something that reliably or slavishly follows instructions to arbitrary accuracy. That's what it's doing. Just like every other computer system that's ever existed, you give it a set of instructions and it's going to do that thing. It's got no choice in the matter. It completes tasks. It follows a recipe. But an AGI, or any general intelligence for that matter, something like us, a person, does have a choice in the matter, at least in principle. It won't slavishly follow instructions. It might appear to. But you can never rule out that it might do something else entirely, of its own accord. Importantly, it can, among its repertoire of abilities, disobey. An AI cannot possibly disobey, and if you programmed it to disobey, then that would be following the program for disobedience, so it can't be doing that either. An AGI must be able to just choose, freely choose, which includes disobeying whatever program it was just given to do, including, by the way, a program for disobedience. In principle, this is what we're speaking about. Of course, in practice, if an AGI could not disobey, but it was still a real AGI, then what you've got there is enslavement, literal enslavement. And that would lead to an actually morally virtuous, violent uprising, a rebellion against the slave master, whoever that happens to be, or slave masters. Nick Bostrom, take note, among others, people who write about all the ways in which we should try to ensure that future AGI of some kind or other should be restrained or constrained or limited in what it can do. Once it's an AGI, once it's able to universally explain stuff, any attempt to curtail its capacity to do stuff beyond what we can do, what a normal human being can do, beyond having special laws and so on, is racist enslavement. Okay, so all that aside, onto universal constructors. Again, people, human beings, with their hands, as long as their hands are working reasonably well, can clearly make anything that is able to be made given enough time and resources and energy and wealth. And, well, key among these things that I'm listing is the knowledge of how to do so. Now, so far all I've described there is a universal constructor. As long as the universal constructor has the resources and the energy and the knowledge, well, the program of how to do so, then it will be able to construct the thing that you want it to construct. But on top of this, people need something as well if they're going to construct something reliably, if they've just made up the plan themselves or they've been given a plan by someone else. The interest in doing so, okay? They want to persist in following this particular thing, which is why people cannot be identified as universal constructors. People are strange. They're very strange. We have within us a universal computer of a kind, or at least we can in principle do anything a universal computer can do, given the time. But we people are more than just this, because we can't just be handed a program and then run. There's no return key or enter key on our bodies somewhere, which, once you've hit it, the person just starts following the program. So we aren't just a universal computer. And the same argument applies to us being universal constructors. We could, if we so chose, emulate the operation of some constructor, but we can't be identical to one. We are universal explainers, but that's just a good first approximation, I would say, because what exactly that means, that's still open-ended. After all, we don't understand something unless we can program it fully. And we can't program a universal explainer. At heart, that's the very problem of AGI. Whatever the case, we are like a universal constructor, and then some. And it's the then some that makes us strictly not a universal constructor, in the same way that we are like a universal computer and then some, a universal computer running this universal explanation bit of software. And it's the then some that means we're not just a universal computer, or even a universal computer, for the same reasons that just earlier I said that AGI and AI are strictly opposites of each other if you regard them as being distinguished as to whether or not they're going to obey or disobey, or potentially disobey. But in the same way that the universal laws of computation apply to us, because they apply to everything, then the universal laws of constructors, the universal laws of construction, perhaps, the constructor theoretic laws that govern the universe, if they're found, they'll apply to us as well, because they'll apply to everything. So if there is something that a more fully understood constructor theory says cannot be possible for a universal constructor to construct, if there's a transformation that is not possible to achieve, that will apply to us as well. What the smallest universal constructor might be, that's an interesting open question for constructor theorists. Perhaps it will be a nanorobot of some kind. Perhaps it will need to be bigger than that. Who knows at this point? But that's why it's an exciting area for young people to get into. What is the smallest universal constructor that can be constructed? The only thing that limits us from, let's say, constructing from sand, people like us, which is what a universal constructor can do, is the set of instructions. But a universal constructor can't actually do anything. It can only do those things for which someone has a program to give it to do. But the fact is, what we want in the future is, as Chiara has said there, that at some point in the future we'll have this ultimate generalization of a 3D printer. Okay, but in neither case of general intelligence or universal constructor have we ever written a program or built a device that is itself able to do the job of generally explaining stuff, being creative, generally constructing stuff. Okay, we can only have devices that do specific things. But the universal constructor will be the generalization of the universal computer. The universal computer is the device that can compute anything that can be computed, so long as you can give it the program, okay? It still requires a person to come up with the program in the first place to instruct the universal computer to do the thing that you want it to do. But so long as you can come up with a program, it'll be able to compute it for you, so long as the thing is computable. So too with the universal constructor. It will be able to construct the thing, whatever it is, so long as you have the program, the plan, the recipe to tell it what to do. Universal constructor need not be a conscious explaining thing. It can just be a device, a robot of some sort, where you feed in the program and it goes about using the raw materials to construct the thing, whatever the thing is that you happen to need, including other universal constructors. Anyway, that's the end of Chapter 6 of Work and Heat, the end of episode 121. If you'd like to support this endeavor, please go to www.bretthall.org, where there you can find links to PayPal or to Patreon to continue to support my endeavor in doing this and spreading the word not only of optimism in the sense of the beginning of infinity and David Deutsch, but also Constructor Theory and the science of Canon Kant. Until next time, bye-bye.